Morning. Can people hear me? Is this better? All good? Morning. Yeah, let's get started. So I think there was some confusion about how to do the sign up for Canvas. So originally it was Monday, but I extended it to today. So please go to Canvas, and I think it's like under people. You just go to the groups and you put your name in one of the groups if you want to. If you don't, that's totally fine. We can randomly assign the rest of the students. But if you do, please do that by the end of today. And then accordingly, the team contract has been extended to Sunday. Okay. And yeah, so also another reminder, please don't directly email me or the TAs. If you have questions, please post on Ed, because one, other people might have the same question. And also it has more chance of reaching more people if more people can see it, because I get a lot of emails. So it is unlikely that I can handle all of the questions directly in my inbox. Any questions, concerns about PA1? Okay. All right, so let's continue. Last time we were doing work span analysis, so we'll try to finish that up today. So last time, recall that we were doing matrix multiplication, and we had done like the simple 3 loops version, and we can put parallel for on the loops, either the most outer one or the 2 at the outer ones. And then, yeah, so we're just doing another type of matrix multiplication, specifically the recursive kind, one for another example of work span analysis, and also because binary forking fits very well with divide and conquer type algorithms. So recall that this is one way to do recursive matrix multiplication. We have an output matrix C that we want to compute. It has 4, this is the base case, it has 4 elements. So C00, C01, 10, and 11. And we have 2 input matrices, A and B, both with also 4 elements. And to multiply them, we can cast it as 8 recursive matrix multiplications. So this is A00 times B00, A00 times B01, and so on. And if we add these 2 up, then that would be the result of what we want to put in C, and that is 8 submatrix calls. 1, 2, 3, 4, 5, 6, 7, 8, and 1 matrix addition. Each recursive call is size n by 2 by n by 2. If we started with n by n, and the yeah, and then the addition is size n by n. This is just about the matrix layout. So the time that it takes to do the operations depends on the matrix layout, like how it's ordered in memory. Because, for example, like when you do the matrix addition, how fast it will take depends on like how fast it takes to access the different parts of the matrix. So one natural way to order a matrix is called row major, which is that like memory is one. You can think of memory as one flat thing. But however, a matrix is 2D, so you can just think of it as like laying out the rows one after another. So like all the elements in row 0, then all the elements in row 1, all the elements in row 2, and so on like that. And so if you want to index into a row, you multiply the row number by n plus whatever column index you want. And if you want to index into an arbitrary submatrix, which is a thing that we have to do, like in the recursive subcalls, then you can index into the row, and then you have the dimensions of the submatrix, and you do a similar type of indexing. Okay. So when we do divide and conquer, we have to identify where the subproblems start. So that's why I was talking about indexing, is because you need to know how the matrix is laid out to do the indexing into the subproblems. And so we have these 4 quadrants, 0, 0, 0, 1, 1, 0, 1, 1. And each of them has dimension n by 2 by n by 2. And you can get the starting point by, if your pointer here is a, then this is a plus n over 2. This is a plus n by 2 rows times n. And then this is this thing plus n by 2. So when you do the recursive subcalls, like originally as parameters into the function, you get like the pointer to a, and then we get the side length. And this is how you calculate the side length and the pointer in the recursive calls. Questions on that part? Okay. So this is the code to do divide and conquer matrix multiplication. This is the function call. We have matrices A, B, and C, and we have side lengths n sub A, n sub B, and n sub C. And for ease, we're just going to think that that the matrices are squared. So all of these are the same, and also they're powers of 2, because cutting them in half is nice when they're powers of 2. So we'll just go through this. This restrict keyword means that the matrices are not aliased, which means that like A, B, and C don't point to the same memory location. Like I said, n sub A, n sub B, n sub C are the row size of the matrices A, B, and C. Yeah, the 3 input matrices have size n by n. And so there's two parts. One is the base case, and one is the recursive call. The base case is just like this. We set some constant threshold. This is called coarsening. So you don't, even ignoring parallelism for a second, when you do recursion, like in practice, you probably don't want to recurse all the way very down to the constant like 1 size, because there's function call overhead, even ignoring parallelism for a second. So you want to amortize the cost of function call overhead against your recursive call. And so that's why we cut off this recursion at some constant. But from a theoretical perspective, threshold is something like theta 1, so it doesn't affect the actual recurrence, it just affects the actual implementation. And this is the base case, so C, A, and B, and you can think of this as just like the 3-loop version that we had originally. Like you can do the simplest theoretical or the simplest serial algorithm as the base case, because there's no further parallelism down there. And in the recursive call, so if we go back a little bit, we need a temporary because we have to add these 2 matrices together. But in the beginning, we only have C. So we need to allocate like a temporary called, we're going to call it D in the code to store this one. And then we have to add them together. So that is why we are allocating D, which is a temporary also of size n by n, so equal to the size of C. And this is just a macro to compute the indices into the submatrices. And then finally, this is the actual recursive part. So there are 8 all to this divide and conquer matrix multiplication. And this is looking a bit complicated, but if we just look, let's just look at this column. So these 4 subcalls are computing the different quadrants of C. And these 4, this last one doesn't have a spawn, but these 4 are computing the 4 subquadrants of D. And each of them has recursive size n by 2 by n by 2, because we cut the matrix into quadrants. And you can just trust me that these A and B are the correct indices. So this is using the spawn and sync constructs that we learned last time. This is 7 parallel spawns, and this one is in the continuation. So you don't need to spawn them all, because there's still one parent thread that's going to run after all of these are spawned, and that one can do the last subcall. And then the sync at the end. All of these need to finish before we add them up. Like we have 8 calls, and then we need to fill them in and then add the 2 matrices. Yes, the threshold is just you can think of it as just some constant greater than 1. And the reason is, it's a performance reason. It's not really like a correctness reason. It's for, like even in ignoring parallelism, you would want to cut off the actual recursive calls higher than 1 because there's function call overhead. And so like at some point, the function call overhead becomes more expensive than the actual subcall cost. So you want to reduce that cost. In parallel, the issue is even greater because not only is there function call overhead, there's also there's cost to do the spawn. like the thread needs to start the other job. So this is just when you write any divide and conquer program, you should cut it off before, like higher than 1. But you can think of this as just something theta 1. So it doesn't affect the theoretical recurrence, because like when you have the theoretical recurrence, there's 2 cases. One is the recursive case, and one is the base case that's like at theta 1. Yes? That is a good question. And you would have to be more careful in your cutting. Yeah, like you could cut it directly in half, but like one side would be slightly bigger than another side. So I think you can still do divide and conquer, but you just need to be more careful both in the cutting and in the base case. And you can also do divide and conquer for rectangular matrices. They don't have to be square. But then you don't cut along both dimensions, you cut along the longer dimension. So there are 8 recursive subcalls. And then after that, we do a sync because we need the results of the recursive subcalls to add up the 2 matrices. The last one, we have this temporary D. We stored partial results in both C and D. And so we need to add the results of D into C. So that's what this is. And then we can free D. And this is just this code for matrix addition. So you have 2 matrices, C and D, and you want to add the element-wise into C. And each element is independent, so that's why there are 2 parallel for loops there. So 1 over I, 1 over j, which are row and column dimensions, and then you can just, in parallel, add them all element-wise into C. Questions? Okay. Yeah, and this is the last bit, you just free it. So we want to analyze the work and span of this entire recursive divide and conquer matrix multiply. But first, we want to analyze the subcall to matrix addition, because when you think about writing the recurrence for this matrix multiplication, the matrix addition needs to be done at every level of the recurrence. And so that is, when we talked about the master theorem, that is going to be what is in f of n. So the work is, of course, n squared, because the matrices are of size n squared, and you have to add them element-wise into C. And then the span is log n in the binary forking model, because the span of parallel 4 is log n. And there are 2 parallel 4s. So when you think of the computation DAG, the outer one goes to log, and then each one of those has log coming off of it as well. So that's log plus log, which is theta log. That make sense? Okay. And so we're going to use that in the work. So the work, again, is just the work, like the time that it would take on one thread. This doesn't change with, you can get the work by just ignoring all the parallel constructs. So you would just ignore spawn and sync or parallel 4, and you would analyze the algorithm like that. So the recurrence for the work, there are 8 recursive subcalls. Each one has side length n over 2. And this theta 1 is just the cost to like cut the subproblems. So you have to do a little bit of indexing. And a sub 1 of n is what we had on the previous slide, which is the cost to do the matrix summation. And that needs to happen at every level of the recurrence and every subcall. So this part is the same. And this is n squared, because we just got that from the sum. And using the master theorem, we compare, so a is 8, b is 2, and f of n is n squared. And so in the master theorem, we compare n to the power log base b of a with f of n. Because this thing, n to the log base b of a, is the number of leaves at the bottom of this recursion tree. And there are n cubed of them. which is asymptotically bigger than n squared. So this is case 1, which is geometrically increasing, so the solution is n cubed. Now we want to compute the span. So the work is just you add up all the subproblems, but for the span, you take the max over all the parallel part. And so all these subcalls, you just take the max and they are all equal length. So this is the expression for the span, m sub infinity, and that's just m sub infinity n over 2. There are 8 of them, but they all happen in parallel. So recall that the span is the longest path through the computation DAG. So all of them are about equal length, and so that's why we just take one of them, because they're all happening independently of each other. And this is the recurrence, so it'd be like you have to do the problem of size n over 2, and then you have to do the problem of size n over 4, n over 8, and so on to the bottom. So this is m n over 2 plus the span of the matrix addition, because you have to do that at every level. And so we just said that the span of matrix addition is theta log n. So this is, again, we can apply the master theorem. A is 1, because there's just one of these here. B is 2, and f of n is log n. And so n to the log base b of a is n to the log base 2 of 1. That's just, the whole thing is 1, because this upper thing is 0. And so we compare 1 with f of n, is n to the log base b of a log to the power 1, because this is 1, and this is log, and this is log. And so, like, this is case 2, when it's arithmetically increasing through the entire thing. So that's like, if your f of n is of the form this thing to the log to the k, or the number of leaves times log to some power k, then the solution is that thing times log to the power k plus 1. That's why it's log squared. Questions on that part? Yes, go ahead. Yes, this is k is 1 in this case. Yes, because we found that the span was log n in the previous slide when we analyzed the addition. And so now we're trying to do the span of the entire matrix multiply. So we're comparing f of n with n to the log base b of a. And we find that f of n fits this form, n to the log base b of a times log to the k n. And in this case, k is 1. This thing also happens to be 1. And then, so like the solution is log to the k plus 1. Mm-hmm. Thank you. Yeah, go ahead. Oh yeah, sure. Look. Yes, so we need to define a temporary, because here, to do the matrix multiplication, we need to add 2 matrices together to get C. And so like we have 2 n squared entries that we need to add together, but we only had n squared output, so we need to make a temporary. Mm-hmm. Yeah, good question. So here, just to recap, the work is n cubed, is theta n cubed. The span is theta log squared n. And the parallelism, you divide the work by the span. That is n cubed divided by log squared. Oh, LG is log to the base 2, which is also theta. Any constant in the base is theta log, but this is more precise, which is LG. And then the parallelism is quite high. So this example, 1,000 by 1,000 matrices, the parallelism is something like 10 to the 7. Mm-hmm. Sorry, could you say it louder? Um, Sorry, I think I can't hear quite well, but my understanding is that the question was about the cases in the master theorem. Uh-huh. Yeah, so the question is like, why is A different in the work and the span? So yeah, so here it is 8 because the work is the time that it would take on one processor. So you can just ignore the spawn part and the sync part because it has nothing to do with one processor. And we are trying to write the recurrence for how much time this will take. There are 8 subcalls. Each one has size n/2, and that's why we got 8 here. And then here, this thing came from the work of the matrix addition, this n squared. Yeah. So going to the span, why is this thing also not 8? Because if you remember, like last time we were talking about like how do you do, like if you remember like the slides with the clouds, and one is like in series and one is in parallel. And for work, both of them are you add them up, but for span, you take the max over the 2 clouds. And for work, you take, yeah, for span, if they're in series, you take the addition of them. And if they're in parallel, you take the max of them. Because the span is the longest path through the DAG. And so like, you don't need to add the span if they're both in parallel. You just take the max over them because it's the longest path. Both of those have DAGs inside, but you take the max over both of those clouds because they come to the same place in the end with sync. And so that's why there's only 1 here rather than 8, because these 8 subcalls proceed in parallel. They don't need to be like one after the other. Did that answer your question? Thank you. Anything else? Okay. So next we'll talk about a little bit different variation of how you can do this matrix multiply. And the reasoning is, so we had to make this temporary, which takes time because you have to allocate n squared space at every level of the recursion. And we have a lot of parallelism. So one way that we could possibly try to improve this is we trade some of the parallelism to minimize the amount of extra storage or temporary that we need. And the reason that we needed the temporary is because we had 8 subproblems proceeding in parallel. So the idea is like, what if we could do like, and the reason for that is like because we had like two matrices that we needed to add up. So what if we just computed the 4 quadrants of the first matrix in parallel, and then the 4 quadrants of the second matrix in parallel? So we give away some of the parallelism. Now we have 2 4-ways rather than 1 8-way, but then we wouldn't need a temporary because we can just directly add into C. Okay. And this is how we're going to do it. So this is a modified version of this divide and conquer that doesn't use the temporary. So rather than 1 8-way parallelism, previously we had 8 subcalls. The first 7 were spawned, and the last one is in the continuation. Now we have 2 sets of 4. One is, each set of 4 has the first 3, which are spawned off, and then the last one is in the continuation, and this one is sync. So this is the high-level plan. We, rather than doing 8-way parallelism, we do 4 of the subproblems, which are in like we have 2 matrices that we need to add to solve it. We compute the first one with 4-way parallelism, because there are 4 independent quadrants. And then we finish that one, and then we compute the second one and just directly add it in. So now, because we had the sync, we can reuse C. So we don't need to reallocate the D temporary. And the reason for that is because the reason that we needed to allocate the temporary in the previous version is because we had multiple subproblems trying to write into the same quadrant. Like we had the 2 matrices that need to be added, and both of them have subquadrants in them. but now we're just computing one of the matrices first and then another one. And so we can reuse C, and we get rid of the need for the temporary. The work is unchanged. This is still n cubed. There are still 8 subproblems. Each of them is size n squared. And now, this used to be theta n squared because we have the matrix addition. But now notice that we don't need to do the matrix addition because in the base case, we can just directly add it into C. So this becomes theta 1. It doesn't change the asymptotic complexity because in the master theorem, we're still comparing n cubed with f of n. And now f of n is 1, which is, again, asymptotically less than n cubed. So all the work is in the leaves, and the solution is n cubed. So it doesn't save us asymptotically in the work, which kind of makes sense because subcubic matrix multiplication is harder than this. But we did pay something in the span. So previously, this was 1 out here because we had 8 subproblems that could proceed independently. But now we have kind of like 2 blocks of problems that can proceed independently. So this is like m infinity, this is like m sub infinity plus m sub infinity, because we kind of did like 1, and then we had to wait, and then we did another one. So that's why there's a 2 out here. But we did save something here, like this used to be log squared, or sorry, this used to be log because of the matrix addition, but now this is just 1. But now we're in a different case of the master theorem than previously. Previously, we were in the arithmetically increasing case, but now A has changed. Previously, A was 1, now A is 2, so we compare n to the log base b of A, which is now n, with f of n, which is 1. And n is asymptotically bigger than f of n, so all the work is in the leaves, and that's n. So we paid a little bit in the span, and therefore in the parallelism, because the parallelism is smaller when the span is larger. The span is in the denominator, so the parallelism is now n squared rather than it was like n cubed over log squared before. But however, it's still quite large, like for these small-ish matrices, 1,000 by 1,000, this is like 10 to the 6. So there's still ample parallelism, even though we have paid some in this case. And in practice, this second version is faster because because allocating memory takes some time. And additionally, there were constant overheads. Like the matrix addition doesn't show up in the asymptotics, but it does cost you something in practice to do the matrix addition, and that is now solved because we pushed all the additions into the leaves. Questions? Hmm? Yeah. Thank you. Other questions? All right. So now we're going to move on to merge sort, just another example of work span analysis. Okay. So merge sort is a classical sorting algorithm where it's again a divide and conquer sorting algorithm, and at each level you have to do theta n work to shuffle 2 lists together. And this is the code to do the merge. So you have an output list C, and you have two sorted input lists A and B, and you want to merge A and B. Both A and B are sorted, and you want to output a sorted list C. And this is one way you can do it. You basically keep one pointer to the start of A, you keep one pointer to the start of B, and you walk them both forward, and you always take the min off the head. And at the end, when you reach the end of both A and B, we will have a fully sorted list in C. And the work to do that is theta n, where n is the number of elements that we're going to merge, because we touched every element once. And that is a core subroutine when we do merge sort. So this is sort of like the quicksort example that we had last time. In merge sort, the base case is just at n equals 1. We have some output vector c. And in merge sort, you spawn, or in merge sort, you have two recursive subcalls, first half and the second half. And basically it works by recursively sorting the two halves. And so in the very end, when you unwind the recursion, you come to the top and you have two sorted half lists, left half and right half, and you shuffle them together to get one sorted list. And that's the end. And so like if you just ignore the spawn and the sync part for a second, this is just the code for merge sort. Like left half, right half, and then you have to merge the two halves. So the work is unchanged. There are two recursive halves. Each one has size n over 2, and it takes theta n at every level to do the merge. So total would be n log n, because there are n levels, or sorry, there are log n levels, and each one takes time theta n. Yeah, and you can prove that through the master theorem. You can also prove that analytically by making an argument about the work that you have to do at every level and the total number of levels. So A is 2, B is 2, and n, the number of leaves is n, and f of n is n. K can be 0 in case 2. So f of n is n times log to the 0 of n, and that now k is 0, so in the solution that's k plus 1, so that's n log n. For the span, we have these two halves. They can proceed in parallel. So again, we take the max over the two subproblems because they're independent. So there's only A is 1, B is 2, because the subproblems are cut in half. And because for now we didn't parallel this merge part, the span is also theta n. Like in the normal merge, you have to walk both of them one by one. And that is initialized, which takes time theta n. Using the master theorem, you can show that this is also theta n. All the work is in the leaves. Or sorry, all the work is in the top. This is case 3. So we have this work, which is n log n. We have the span, which is theta n. And then if you calculate the parallelism is log n, which is a problem because ideally we would like the parallelism to be much larger than p, which is the number of processors that we have. And log n is small relative to p, usually, unless your n is like very huge. But for most reasonable n, like log grows pretty slow. So you want to parallelize the merge part. Mm-hmm.
So just on for like the span, the reason why it's like t of n over 2. Like if you want to choose, isn't probably because it's being divided up into a parallel problem.
Yes. Yeah. Yeah. Like remember like that slide with the clouds from last time? There are two cases. One is like the clouds are one after the other, and one is that the clouds like there's two like this, and we're in the case where the clouds are like this. So both of those sides are n over 2, but because they can proceed in parallel, we can take the max over them because the span is like the longest path through both of them, like the max over the longest path through both of them. The path is this t n over 2. Thank you. Yeah, so this is a good point. This is like maybe a hard thing to understand about span, which is like when do you take the sum and when do you take the max? And the way to see it is kind of like if they're together before a sync, maybe one way to think about it is like then you take the max because they're occurring in parallel. But if there's like in the example that we just had with the matrix multiply, we had like a bunch of spawns and then a sync and then a bunch of spawns and then a sync. And in those cases, we had to add the two blocks together because the sync means that you have to wait until the first block is finished until you can continue. So the next part, we're going to parallelize this merge, because that is our main bottleneck in parallelizing this entire thing. So this is, I don't know, I think it's kind of like a cute algorithm, just like a little nugget. So the way that you parallelize the merge is that you have these two lists that you need to merge, A and B, and both of them are sorted. And we want to divide this, again, recursively into two halves, such that we can merge in both the left half and the right half, and that they both fall into like the same range. So that all the elements in the left half will be smaller than all the elements in the right half. Because then we want to, again, like when we unwind the recursion, we would want to have this property. And the way that we're going to do that is, because both of these are already sorted, we can leverage this property. And this is sort of like a little bit like quicksort partitioning, in that you take the midpoint and you look for the midpoint. You're trying to merge these two lists, A and B. You take them, let's just say that A is bigger without loss of generality. You take the midpoint in A, you search for it in B, which you can do efficiently with binary search because B is also sorted. And now you have two halves, left and right, both in A and B, where the left half in A and B is smaller than the midpoint, and the right half in A and B is bigger than the midpoint. And so now both of these halves, like you can do a recursive call with both halves, left side and the right side. And both of them can proceed independently because you have this guarantee that the stuff on the left is smaller than the pivot and the stuff on the right is bigger than the pivot. And the idea that the way that we're going to, the proof is like more complicated, what you'll have to do, but the way that the proof is basically going to go is that you want to show that with this cutting scheme, the number of elements decreases by some constant factor every time. So in that way, we can bound the height of the recursion. And you may, and like indeed, there is some worse where like we midpoint at A, and then maybe only one element in B is less than that midpoint, and then all of the rest of them, or even none of them are less than that, and all of the rest of them are greater than the midpoint, or vice versa. And the way that we can prove this 3/4 is that A is greater than B, or A is bigger than B, and so A is at least cut in half. And so this thing can at most contribute the size of A, which is half the total size, or at most half, at least half the total size. Does that make sense? All right. This is the code. So we have this output matrix, output list C. We have input list A and B. And if A is smaller than B, we're just going to flip them. So this is just, again, returning into the recurrence, but we're setting A to always be the larger one, just for, it's easier to think about that way. And if we're in the base case, A is empty, then we can return. And the recursive case is you pick the midpoint in A, you search for it in B, and then you know that the midpoint in, like, you know how many elements are going to be total in the left half, and you know how many elements are total going to be in the right half. And so this is just setting that point in C to be the start of, to be A's midpoint. And then we spawn the two halves, merge left half, merge right half, and then sync. Mm-hmm. If A is empty, why do you set? Because A is always the larger one. And so if A is empty, B must also be empty. Thank you. Yeah, good point. Yeah, there's a subtlety, which is like this came first. And so, yeah, then A is always the bigger one. Yeah. Does this make sense? This is a bit subtle. Maybe it's not super obvious up front. I can do this. So first, we can calculate the span. And I said earlier that the problem will be at most 3/4 times what it was previously in the recursive case, because the argument is like this. A is the bigger one. We cut A in half, and so like the total size of the problem is the size of A plus the size of B. And we chose A to be the bigger one, so A must contribute at least half the size to the problem. And we cut A in half, and even if B is fully recursed again in the lower subproblem, that contributes at most half to the size of the problem. So we cut the problem by reduced it by at least 1/4 size. So that's why there's 3/4 here in the recursive call, and that's plus log n in this part, because the binary search has span log n. And we use the master theorem. A is 1, B is 4/3, and we compare it. Yeah, but it doesn't matter what's in the base of the log, because A is 1, so this thing is just 1. And then we're in case 2, k is equal to 1. The total solution is log squared. So that was good for the span. We reduced it from n to log squared, but now we want to make sure that the work is still fine. And this is not in the master theorem cases, because in the work, at every level, there's 2 subproblems. Each one will be cut by some constant, but there's like 2. Let's just call it alpha, which is how much the difference between each subproblem is. One side is alpha, one side is 1 minus alpha, both of them times n. And then the work, this extra part is log n because of the binary search. And we do have some bound for this alpha, because like similar to the argument that we made for the span, we know that it's between 1/4 and 3/4. In this one, we're parallelizing the merge part. So this is only about the merge. We're going to use this as a subroutine in the higher level merge sort. And the reason that we're doing all this is because when we just did like this 2-finger stepping in the merge, the span of that is n. And so that's basically serializing the entire thing. We found that the parallelism was log n, which is very small. So that's why we're doing all this. And so right now we're just focusing on the merge part. We have shown that the merge has span log squared, but we don't want to lose in the work, and we want to show that the work is also still theta n, which is what it was before when we did this 2-finger stepping. It was of course n because we touch every element once. It's a bit complicated, but you can prove this through substitution. Yeah. Basically, we want to prove that it's theta n, and you can by choosing some appropriate constants. Maybe you don't really want to go through this. It's not really the point, and we will not have to do this on like the homework or anything. So the point is that you can show that it's theta n. And that kind of makes sense because you're not doing additional, like in the recursion, you're not really doing additional merging than we did in the serial case, because we still touch every element at most once. But this is just proving something that we can like kind of intuitively feel. And now going back, so for now we're just focusing on the merge part because that was the bottleneck. The work is theta n, the span is log squared, and the parallelism is n over log squared. And now going back one level up to the entire merge sort, previously this was just merge. We plug in parallel merge here into the sort. The work is unchanged. It's still n log n. Now the span is changed. Previously, this f of n was theta n, which was a problem. Now it is log squared because we did all this work to do this recursive parallelization. And we are again in case 2 of the master theorem. K is equal to 2 here. And so the total span of the entire thing is log cubed. Because the solution is with k plus 1. Yeah, so going back up to the entire merge sort, the work is n log n, the span is log cubed. You divide them to get the parallelism, that's n over log squared. Which is much better. Previously, this was only log. Questions? Yeah, okay, so just to wrap up that part, the parallel merge is cute. I think maybe if you remember one thing about the merge sort, it could be the parallel merge. The higher level is that problems that look serial, like the merge, it kind of looked like it depended on going through the entire thing. But if you leverage properties like sorting, maybe you can, in a smart way, split it up into independent subproblems. Okay, so this is the last part of workspan. We are going to do one more problem. It's called Tableau construction. And the problem of Tableau construction is like this. Suppose that you have an n by n Tableau that you need to fill in, where this entry aij is some function of the neighbors, aj minus 1, ai minus 1j, and a like the up neighbor, the left neighbor, the up left neighbor. And this is like a common paradigm in dynamic programming. So often, like, for example, like edit distance or longest common subsequence or stuff like that. Each entry is a function of your left neighbor, up neighbor, and up left neighbor. Like for edit distance is like substitution and insertion and stuff like that. So we have to fill this n by n grid, and we want to do it efficiently in parallel. In serial, the work is n squared, because we have to fill in n squared slots. And each one takes constant work, assuming that f takes constant time to do this comparison. To do it in parallel, we can cut it like this. We have an n by n grid, and we cut it into 4 subquadrants. And the reasoning behind this is that we need to maintain the dependencies. Like when you compute each slot, the correct neighbors like left, up, up, left need to be finished before we solve any particular slot. And so this is one way you can cut it. This is the first quadrant. These 2 and 3 can be done in parallel, and then 4 depends on. So 2 and 3 depend on stuff in 1, but they don't depend on stuff in 4, because it's just like left, up, left. And 1 depends only on stuff in 1, and 4 depends on stuff in 2 and 3. But if we have already solved 2 and 3 first, it's no problem to solve 4. And so this is like the high-level picture of what it looks like. First, we do this entire subquadrant. Then in parallel, we can do this part and this part, which are independent because they have everything they need. Like 3 needs stuff here, 1 needs stuff here, or sorry, 2 needs stuff here. And so then we sync. And finally, if 2 and 3 are finished, 4 can go ahead because it just needed stuff here and here. Yes? Okay. What is the recurrence for the work? Remember that the side links are n. Yes. Oh, sorry. I meant like in terms of t, but yes, the solution should be n squared. Like, how many subproblems are there? Not like what is the size of the subproblem? Like how many recursive calls are there? 4, because each one of these quadrants is one recursive call. And the side length of each one of these is n over 2. So we're just going to cut it like this. Because it's in the continuation. So like after you spawn 2, there's still one thread that continues. And so that one is going to do 3. So you don't, it's not totally incorrect to spawn them both off, but then the parent thread has nothing to do and everybody has to wait. So like the parent thread would create 2 new ones to do 2 and 3. Whereas like it could be like it creates 1 to do 2 and then it itself does 3. So the work is, there are 4 subproblems. So A is 4. Each one has size n over 2. So B is 2. And then it costs theta 1 to like find the indexes to do this cutting. And the number of leaves, n to the log base b of a, is n squared. F of n is theta 1, and n squared is much bigger than f of n. So the solution is just f of n. The solution is just n squared. So this is good because originally it was n squared. So like if we just did it in serial with loops, that would be n squared, and we don't like, we want to design work efficient algorithms, which means that we don't do more than a constant factor of work compared to a serial algorithm. So this is a good sign. We're doing asymptotically the same amount. Okay, and what about the span? Could you say it again?
T of n over 4 plus what of theta 1?
T of n over 4 plus theta 1. So there is some dependency between the subproblems. Like if it was just t of, if it was just like a 1 in front of the t, that would mean that all the subproblems can proceed in parallel, because we would take the max over the span through all the subproblems.
Because t infinity of n is 2 times t infinity n over 2. Now, because we have 1 and 4 have to, you only get to, for a given node, you only have to do its 2 and 3 parallelly. So maybe I'm undercounting actually. Maybe it's 3. Yeah.
Yes, exactly. So yeah, does that make sense to people? So the reason behind this is kind of like if you think back about the matrix multiplication thing that we were doing when we had two groups of them, and each one of those groups could also proceed in parallel. So each one of those contributed t infinity n over 2. Now we have kind of like 3 phases. 1, like they're different colors. So like 1, and then 2 and 3, and then 4. So you can kind of think of it like there's like kind of like this diagonal front moving through the quadrants from upper left to lower right. And so there are 3 of them. And so this is 3 t infinity n over 2 plus theta 1 to do the cutting. And that is n to the power log 3, because the number of leaves is n to the power log 3. F of n is theta 1, and this thing is bigger than theta 1. So the way that you derive recurrences for span is you can think of like how many, in some sense, like how many parallel phases are there. And in each of those, like if you remember the clouds, those parallel phases are proceeding in serial. So you need to add them up. But within them, you take the max over whatever problems are happening within the phases. And that each of those is contributing this t infinity n over 2, and there are 3 of them. So that's why this is 3 times this thing. Yes, yeah. So 1 contributes t infinity n over 2. 2 and 3, they're happening independently, so they both together contribute just a single t infinity n over 2, and then like if you think of the cloud, it's like 1 and then like 2 like this, and then 1 again like that. There's like 3 in this wavefront. Okay, so we have the work, which is n squared. We have the parallelism, which is n to the log 3, and, or sorry, the span, which is n to the log 3, and the parallelism, which is something like about n to the 0.4. But there's no reason that we had to cut it into quadrants. Like you could cut it 3 ways in each dimension rather than 2. Quadrants is easy to think about, but like the same idea applies. Like basically what happened in the quadrants was that we cut it into 4, and then we solved 1, which had only dependencies within itself. Then we used whatever we solved in 1 to solve 2 and 3, which has dependencies in 1. And then once we finish 2 and 3, we can do 4, which has dependencies in 2 and 3. We can do like a similar, like this is like the minimal case of this approach. Basically what we did was like we started from the upper left, and we kind of moved like in like a front from upper left to lower right. And 2 by 2 is one way to do it, but we couldn't do 3 by 3. And so like the idea is sort of similar. Like if you just look at these 4 quadrants here, like this is the same as the 2 by 2 thing. We have this, these 2 can proceed in parallel, and then this one has dependencies in 2 and 3. But because we cut it into 3, now this entire diagonal can be solved in parallel because it only has dependencies in 2 and 3. And then again, 7 and 8 has a similar thing, and 9 finally. So this looks a little bit more complicated, but we can solve it. So first, we want to make sure that the work is unaffected. So how many subproblems are there? 9. And what is the size of each one? Yes, good. So we have 9. Each one is n over 3. This is the same again. The master theorem tells us that the number of leaves is n squared. It's n squared. So that's good. And that makes sense because we didn't add any more compute. We just cut the subproblems smaller. And the span? Mm-hmm. Good. Yeah. So the number of, if you think about like the clouds, it's like 1 and then 2 and then 3 and then 2 and then 1, and the number of phases was 5. So that's why there's 5 here. Each has size n over 3, and then the total span is n to the log base 3 of 5. Sorry, this should say 5. I'll fix that. So the parallelism is this. This should be n to the log base 3 of 5. I'll also fix it. So it'd be n squared. N to the log base 3 of 5 is something like n to the 1.47. And so if you calculate the parallelism, you divide again. This is like about n to the 0.5. And if you remember before, it was like n to the 0.4. So we increase the parallelism by increasing the divide and conquer ways. One problem with this is that it has less cache locality because you cut the problem smaller. And that it's something that we can analyze later. Mm-hmm. Here? It could be theta. Yeah. Yeah, I will fix this. This should be n to the power of this. Mm-hmm. Mm-hmm. Maybe you'll see in the next slide. It's like a question that you can work out on your own. Like, what is the maximum amount of parallelism if you keep increasing the ways? Is there a limit, or is there some endpoint? Yes. So if you cut it into four, this entire subproblem, if you cut it into four, the entire subquadrant was one single subproblem. But now if you cut it into 9, each subproblem is smaller. So like how do you say this? In some sense, like the independent work that needs to be done on the different processors is less related, is smaller, and so like it has less access to like other stuff in the subproblem. We can formalize it later on because the next topic is MPI, but after that we will talk about caching. So maybe we can come back to it after we talk about caching. Thank you. Good. Other questions? Okay. And this is the last slide for this part, which is related to your question. What is the maximum parallelism that you can get for Tableau construction using divide and conquer in binary forking? So we were only using these basic constructs like spawn, sync, and parallel for. And yeah, this is like without using something fancy like blocking or anything like that. I'm not going to answer this question. This is a question that you can think about on your own. Yeah, and that is it for this part. So we're going to do MPI. Okay. We have about 15 minutes, so I don't think that we can finish this, but we will start and then we can finish next time. So I think the paste cluster is currently down for maintenance, but it will be back on Friday. And then you can start the homework then, but we will finish this lecture on MPI next class as well. Okay. So MPI stands for Message Passing Interface, and it kind of came out like in the 90s or so. Yeah, in 94. So before 94, there are a lot of different standards for software for writing parallel programs, specifically for distributed memory programs. And in 94, people released MPI 1.0. And it's this programming abstraction that can work both in distributed memory and in shared memory. And standards are good because it's good to write portable code. And if everybody agrees that they can run MPI, then your code will run on many different machines. So in message passing, this is like some paradigm for distributed memory programming, but it also, like I said, it will also work in shared memory. But logically, it is distributed in that all communication and synchronization require subroutine calls. So you cannot synchronize through memory, and synchronizing through memory requires shared variables. That means like different processors can access the same variable, and maybe they can do something different depending on what they see in the variable. But in MPI, there are no shared variables, and everybody has, even if everybody has like a different copy of what they call the same name, it is a different variable on every processor. So like every processor may have something called X or A or something, whatever it is, but those are not shared between the different processors. And yeah, the code looks very much like a regular C or C++ program, except for the calls to the message passing library, which we will see. And the most important subroutines in MPI are for communication, which is like sending data between the processors. And there's different kinds of communication. The most basic one is called point communication, which is send and receive. So like you have a source processor and you need to send some data to a destination processor because maybe the source processor has computed something that the destination processor needed. And then there's also these basic, they're called like communication primitives or collectives, which are sometimes there are types of communication that need to involve all the processors, and that's called collectives. So the most basic one is called broadcast. So broadcast is like one processor has some data, everybody needs to get that data. So that one processor broadcasts the entire thing up to the other processors. And there's many others that we will talk about in a later lecture. And some of them are just sending data, and some of them can also do a little bit of compute, like sum, for example. the sum example that we were talking about in a previous lecture, everybody has some number, and then they want to add them all up. And there, it turns out there's an MPI function that can do that. There's also synchronization, which is like everybody needs to reach this point in the code before anybody else can continue. And then there's some basic metadata inquiry, like how many processors are there, or which processor am I, or like, are there any outstanding messages, stuff like that. Okay, so this is how you run MPI. In your code, you include mpi.h. And then to compile it, I think we provide all of this. Like, you don't really have to know this, but maybe just in case you end up wanting to write MPI on your own, you include mpi.h, and then there's some header stuff that I will show you momentarily. And you can use an MPI compiler, such as MPI-CC, and this is just hello world. And then to run it, you use srun. So I think in the homework, it shouldn't hold you back, because in the homework we provide the makefile and also the test driver. So you only need to write the actual MPI part. You don't need to like set it up. So the most basic construct in MPI is called a communicator. And the communicator is like the universe of all the different processors. And this is the picture. Like, you can just think of it, all the processors here, 0, 1, 2, 3, here up to 9. So there are 10 processes. And the default communicator at the beginning of an MPI program is called MPI ComWorld, and that includes all the processes in the beginning of time. And each process in the communicator has a rank, which is a unique identifier, starting from 0, going up the number of processes. And then, so when you write MPI commands, usually you need to provide the communicator that the MPI command is running in. So which world are these processes in, even if it's point-to-point communication. And definitely in collective communication, because in collectives, everybody in the entire communicator is participating. So you need to specify which world is participating. This MPI ComWorld is something that's just given up front. So it's just given at the start of the program. The rank, like I said, is a unique integer identifier somewhere between 0 and number of processes minus 1. And it's used to distinguish the different processes from each other. So you can query the size of the world and the rank like this. So you give these blank integers and you pass in a pointer to size, and this will tell you how many processes are in the world, and this will tell you what rank am I. And MPI ComWorld, so in the beginning you have MPI ComWorld, but we'll see later, like you can make different communicators if you want, but you have to pass in the communicator, which is the universe, to tell you how big is the universe and what is my rank in the universe. And the reason that you would use the rank is later on when we talk about how you send and receive stuff, you have to pass in which rank is sending and which rank is receiving. It's natural, because like how else would you know where the data is going? And also sometimes, depending on your rank and how you write the algorithm, you can say some rank should do this and some rank should do that. So they may do different stuff. So there are 6 most basic MPI commands. The first one is MPI init, which is, you have to call it always at the start of an MPI program to initialize the MPI computation. Finalize is something that you always call at the end of the computation. These are both in the test driver probably already. Com size, which is how many processes are in this communicator. Com rank, which is which rank am I in the communicator. And send and receive, which is sending some data to a different process and receiving some data from a different process. And using send and receive, you can implement like all the higher level MPI functionality. So this is how you would write some basic hello world and MPI. So this is your main function, and we included mpi.h. And for init, you can just put null in here for now. So this is something that has to be at the start of every MPI program. is MPI init. And this world size is how many processes are in this communicator. So in the beginning, you can just pass in MPI com world. Like notice that it didn't need to be initialized anywhere. It's just given from MPI, and this world size is how many processes are in the entire universe. The rank is given by MPI com rank, so you pass in, it'll just fill in this empty integer that you give it. This is telling me what rank am I in the entire world. You can also get this processor name, which is like the name of the machine. You pass in a string. And then this hello world is printing like, this is the processor name, this is my rank, and this is the total number. And then finalize is just at the end of every MPI program. Yeah, I think I'll show you maybe, I don't know if the next slide or in a couple, just like, you can think of every processor running one copy of this program between init and finalize. But of course, like the processors will give you something different for the rank, but like they're just running the same code, but they may get a different answer depending on like, they will all get the same world size because they're all in the same world, but they will get different ranks, and they may have different names depending on where they are. Oh, rank is just a number, and name may be like whatever the server is called. Like the server has, you know, when you set up a server, like it has a name, like a string.
There are certain word size. There are certain
The name may not be all the same for the different processors in the world. Like there may be different nodes in the MPI world. Like the processes may live on different machines, and the machines may have different names. They can be all on the same computer, but they may not all be. Oh yeah, okay. So this will probably answer your question. The way that you can think about it is that this same program, like this in this example, this hello world, is executed on every single process, just copied and repeated. And this is some example output that you would get. So this is how you would run this thing. This is how you use Slurm. You probably learn this in the, if you don't know this, you can learn this in the review session and by also looking at the slides. So the Salak is asking for a interactive node, and then you can run the job using srun. And this is an example output that you might get from this hello world. So this N2 means that I asked for 2 nodes, which are like 2 different computers. And here, this is saying these are the names. Because it's run on Slurm, because it's on paste, this is what they call them, like ATL some number. So this is like ATL0 and ATL1. So there are 2 computers. One is called ATL0, one is called ATL1, and they have some processes on them. Each one has 4 processes, and so the ranks are like this. And one thing you usually don't ever really need the name, but it's just something that you can get out. But the ranks don't have to come in order because they are all executing in parallel. Yeah, I think we should stop for today. Or, yes, right? Thank you.